Hello everybody, I'm Belloni. I'm an electrical system engineer at the Swiss Space Center, and I will present you the communication subsystem of CUBETH. The work I will present here was done by our students during the last year. Initially, what is CUBETH? CUBETH is a 1 unit CubeSat in development in Switzerland. It's a huge project that involves many parts of Switzerland. It's led by ETHZ in Zurich, that they are in charge for the science part and design of the science algorithms. We have Fachhochschule in Luzern, that is in charge for the electrical design of the payload and for the ground segment. There is Fachhochschule in Rapperswil in charge for the antennas, and the Swiss Space Center that is in charge for the platform itself. And we have many industrial partners too. The main goal of the mission is to do a precise orbit determination, comparing GPS, GLONASS, and possibly Galileo, if you will there. There is other experiments that we want to perform, like attitude measurement of the satellite using the 4 antennas, comparing the different measurements, or radio occultation, reflectometry, air density measurement during the re-entry. This mission requires high data rate compared to SwissCube, that was the previous mission that the Space Center has. We will use the same frequency, that's UHF radio amateur band for the downlink and VHF radio amateur band for UHF for the downlink, VHF for the uplink. The power consumption is quite limited. We have less than 150 milliwatts in receiving mode and less than 3 watts in transmitting mode. As I say, the data rate has to go up to 9.6, for the uplink it's 1.2. This means that we cannot reuse the design that we had in SwissCube because it was designed to work at 1.2 kilobit per second, and we need to update it. And we want also to have a better receiving sensitivity, and we want to implement forward error correction. SwissCube, we had this nice mission that was launched 5 years ago and is still working space. We download more than 200 images. We have 5 years of telemetry data. It's now operated by a radio amateur, and we can say that the downlink worked quite well. We have some main problem on the uplink due to the low receiver sensitivity, that is minus 100 dBm. And when the transmitter switched on, the receiver sensitivity decreased even more at minus 94 dBm. And we have most of the uplink commands that are rejected because they contain errors. And we also see high drift on the frequency due to the temperature. That's why we decided to do a new design, a bit different. Here the idea was to reuse some component from SwissCube, but try to find a new component that can reduce the RF part. And what we found a modulator integrated circuit that can do modulation and demodulation, that is quite compact, can perform everything. Then we have a transmitting chain with IC modulator, and then a transmitting power amplifier, it's the same as SwissCube. On the receiving side, we just have this integrated circuit that goes directly to the microcontroller. At the beginning was planned to use the same as SwissCube, but it was not enough powerful to perform all the coding and decoding tasks. And we also have some power interface, same as SwissCube, and I2C interface, that's a new one. And to correct the drift problem, we have a single temperature control oscillator for downlink, uplink. Then you can see if you have a drift, it will be the same on downlink and uplink. That's not the case yet. And also, as the number of the components is quite reduced, it was possible to implement 2 complete boards on the same PCB, and And then we have a code redundant system. That is when one is switched on, the other is off, and if you switch on the other one switch off automatically. And this is a simple node that's come from SwissCube Heritage 2. We had the first version at the beginning of this year. We could test, especially the software. We could implement the coding and decoding software, I2C interface with the old microcontroller, and test the software interface between the microcontroller and the modulator IC. We could also test transmission and reception with external boards. I will show later the results. We have mainly one problem that's due to a routing error. The power amplifier was not working, and it was not possible to correct by hand this error. We have other problem, like the MSP microcontroller that we are using could not reach the 8 MHz due to the power supply that we are using. We need 3.6 volt to work at 8 MHz, and we have only 3.3. Also, due to the limited number of interfaces on the MSP, it was quite complex to interface a single MSP with two different transceiver IC. On the test that we perform, we try to optimize the software using our board and to the evaluation board with the same components. The design that we had, it was possible to skip the power amplifier, then you can test everything, just you have less power. You could test different modulation. You have two FSK. You see that you use a huge spectrum, and then you use a Gaussian FSK that reduces a lot the use of the spectrum. That's quite good because the UHF band is quite polluted now. And we are working now on the second version. It's in production yet. We changed the microcontroller using a more powerful one from the same family with more interface. We correct the routing problem on the power amplifier, and we implement the fully redundant design. And then we could use an SPI interface for the transceiver, the transmitting and the receiving IC. Quickly on the coding, we had to move from IX25 protocol to a ECSS compatible one. That's at least you want to use forward error correction. You can use FX25 if you prefer to use ECSS. For the uplink, we had the BCH code with the pseudo randomizer. For the downlink, Reed-Solomon with convolutional and pseudo randomizer. We'll have more detail on the presentation after mine. And the result on the implementation, we run a lot of optimization. At the beginning, with the first microcontroller, we can run the downlink at 700 bits per second, as our goal was 9,000. That's quite low. In increasing the microcontroller speed, we could increase a little bit this data rate, but was not enough. Then we had to work a lot on the software optimization, and again we could reach the desired speed. On the uplink, we had a lot of problem at the beginning. That's when it's low, that means it's a lot less than 1.2 kilobit per second. And at the end we find the error, and now we can see that we can easily reach more than the 1.2 kilobit per second required. In conclusion, thanks to the integrated circuit that we are using for the modulation, the number of discrete components are drastically reduced, and the performance are drastically increased, especially the receiving sensitivity. We had minus 100 dBm for SwissCube. We are minus 120 here at the moment. The frequency stability is a lot increased thanks to the use of temperature constraint oscillator. We demonstrate almost all the function, and the requirements are met. Just the transmitting power that need to be demonstrated yet, but we have heritage from SwissCube, and we know it will work without a lot of problems. We had a strong involvement, students' involvement and interest, it's not easy to manage the knowledge transfer between students from semester to semester, because quite often they come for one semester and then they leave, and you have a new one that has to continue the work from this one, and he has to restart from zero and spend a lot of time to explain everything. But that's it. It's part of CubeTH team, and thanks for your attention. If you have questions.
Are there questions? No questions? So it was very clear. Thank you very much.